Draw V out for the sinusoidal, a voltage and the input. Since we have a diode circuit, the first step that we have to take is to identify the nodes before and after the diode. So before the diode, I have this node. I'll call this node N, and I also have the ground over here. Now, why did we do this? In order to identify the conditions for the diode. So the diode has two conditions, either it is off or on. If the diode is off, then this condition must hold true. Vn minus 0 must be less than, what is the VD on? 0.7, so 0.7 volts. If the diode is off, it is nothing but an open circuit, so no current flows over here anywhere. Notice that between N and the ground is essentially 1 and 2 resistors. This is an open circuit. Notice also that between V in and the ground is 1, 2, 3 resistors and these N nodes in between. That means that I have essentially a voltage divider. Vn is going to be equal to the ratio of the total resistance between N and the ground, which is 1 and 2 kilo ohms, over the total resistance Sine between the voltage input and the ground, which is 1 plus 1 plus 1, 3 kilo ohms, times the input voltage. This is a voltage divider from circuit theory. Now, very, very easily, I can deduct a condition for the input that tells me that, you know what, when the input is this, the diode is off. True over 3 V in is going to have to be less than 0.7. That means that when V in is less than 0.7 times 3 over 2, which is 1.05 volts, when the input voltage is less than this voltage, that means that the diode is off. Alright, now how much is V out? Again, following the same logic, we have a voltage divider. How much is V out? V out is going to be equal to the total resistance seen between V out and the ground, which is 1, over the total resistance seen between the inputs and the ground, which is 1, 2, 3. This is kilo ohms, which get simplified. All of this times the input voltage V in. So V out is going to be 1/3 of V in. So whatever we have at V in is going to be followed and scaled down by a factor of 3. That means that our signal, when the diode is off, when V in is less than 1.05, is going to look like 2 over 3 times our sine from over here. Now I can confidently assume that when the voltage is higher than 1.05, then the diode will be on and something else will happen. Now I'm tempted to go ahead and draw the output signal over here for the voltage is lower than 1.05, but I will stay patient for now. Now let's see, what if this diode was on? In that case, this condition must hold true. Vn minus 0 must be equal to 0.7 volts. In that case, we don't have an open circuit over here anymore. We have a battery, a voltage source with these polarities of the value of 0.7 volts. So it's just like having a battery in our circuit over here with a constant voltage, Now this simply means that Vn will be always 0.7 volts. Now I can do many things over here. Well, what if I say there is a current that flows from the input to these nodes? For the resistor is going to be 1 kilo ohm. Alright, remember this is not 1 ohms, this is 1 kilo ohm. 1 kilo ohm is going to be V in minus Vn over this current I1. I probably know Vn. It is 0.7, we know it, it's constant. V in is going to vary with time, but we are going to know it. Now, how much is this I1? Well, this I1 comes inside the N node and then splits into 2. Notice that the current that would flow from these nodes all the way to the ground, so let's name this I2 perhaps. Well, this current is strangely not going to be affected by the input voltage. We understand why. Because there is going to also be a third current over here. Let's call this I3. And this node N, is going to always have a constant voltage of 0.7 as long as Vin is high enough. If Vin is more than this value that we have found previously, no matter how high it is, even if it's 100,000 million volts, the current here, I2, is going to be one and the same, always, some value. And that also means that since this current is going to be constant, this V out is also going to be constant. It's going to also have a constant value. The excess current that is going to be created from the rising input voltage is going to have to flow from this point through the diode all the way to the ground. Now we see why this type of circuit is useful for protecting other circuits. There are other ways to protect circuits too from high voltages, but this is a very intuitive way for us to understand it. Now I'm not going to do any math over here to calculate this current because we don't have to find it for this exercise. I'm going to erase this for now, and I'm going to notice again that I also have again a voltage divider. But we must be very careful. We cannot take a voltage divider with this V in all the way to the ground. Why? Because this current that we have found before, I1, is splitting into something over here and over here. And this is not a quantifiable resistance. So things are going to go a bit crazy. It would not be correct for us to take a voltage divider, but we can take a voltage divider from these nodes all the way to the ground because this current is starting from here and flowing all the way to here. So we are correct in doing it like this. So the voltage at V out is going to be Vn, the total voltage, times 1 over 1 plus 1. So 1 over 2. That means that V out is going to always be 0.35 volts. Always. We see that it doesn't depend on the input voltage, and we also understood why. Since this current is always going to be constant, so this voltage divider is always going to give us the same value, since the voltage at this point, Vn, is going to be always 0.7 volts, since the diode is going to be on, since the voltage at the input is going to be higher than 1.05. Now we are ready to draw our output signal. I'll use this color, and let's see. Well, what are our key values? We have 1.05, let's say somewhere over here. From this point onwards, the diode will be off if the Vin is higher. That's fine. Now, how much is the height of V out, ideally? It's 2 over 3 times the sine wave. So this is about 0.67. Also with the negative over here. That means that there is a height over here and over here, that if the output was a constant sinusoidal, it would have to have this output and would also have to have the same period. We see that the period does not change with these configurations. Now, there is a good question onto, well, I see that the output follows the inputs, okay, up until a point, and then does something else, alright? That point is the point where the output voltage is going to be 0.35, somewhere around here. That means that I don't have to do some complex algebra over here to understand when and where. I know that in these configurations our voltages are continuous. So that means that when the rising voltage reaches this point over here, we're going to have the constant output. So we have an input voltage over here, we follow it up until this point. If we had a typical sine, it would keep going upwards up until this point, but now we must have a constant voltage. So we have a constant voltage over here. This is not a constant voltage. We have a constant voltage following it like this. Vin, we see it's still high, very, very high, up until this point again. So we're going to have a constant voltage over here, and then we follow the sine once more. Now, in the negative axis, we don't have anything inhibiting us. So again, now we're going to have a complete half circle. Okay? Again, we reach this 1.05. Our value is going to be somewhere around here, like this, and then we have a constant voltage once more. This is supposedly a constant voltage like over here. So we have something resembling a half-wave rectifier approximately. This circuit is going to be useful for protecting some type of delicate circuitry over here, perhaps transistor or something else, that requires the voltage to be from one point and lower. We cover more diode exercises in this channel, so check out this video or this playlist right now. Study well and take care. Goodbye.